July 1st, 2025, Rio Hurtado, Chile, an automated telescope spots something moving wrong. Not asteroid wrong, interstellar wrong. Velocity 61 kilometers per second. Trajectory hyperbolic, eccentricity 6.1. The math doesn't lie. This thing came from outside. They call it 3I Atlas, third confirmed visitor from another star system. And it just did something at the sun that has never been documented before. You think you know comets, ice ball, coma, tail, predictable physics. But when the object crossed behind the sun on October 29th, 2025, instruments caught it accelerating in ways gravity alone cannot explain. 4 arc-seconds off. Predicted position: brightness, surge, scaling inverse to distance at the power of negative 7.5. Color shift from red to blue, bluer than the sun itself. And the chemistry: carbon dioxide to water ratio of 7.6 to 1. Highest ever recorded. Not even close. If you value documented deep space chemistry and orbital mechanics like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Astrophysical Journal, Letters peer-reviewed study by Martin Cordner and NASA Goddard team published September 26th. 2025, detailing James Webb Space Telescope NER spec observations at 3.32 astronomical units, and the Archive preprint 2510.25035 by Chicheng Zhang from Lowell Observatory and Carl Batams from U.S. Naval Research Laboratory. Posted October 28th, 2025, documenting rapid brightening observed by Stereo, SOHO, and goes 19 satellites during solar conjunction. Now back to the information. Atlas survey picked it up at 420 million miles from the sun. Visual magnitude 18. Moving through Serpens Cauda, near the galactic plane where star density makes detection brutal. Pre-discovery images show it was active way earlier. Zwicky Transient Facility caught it June 14th, 2025, at 6.5 astronomical units. Already producing dust. 5 kilograms per second in early May at 6 AU, 30 kilograms per second by mid-July at 4 AU. That's not asteroid behavior. That's cometary outgassing, turning on at distances where carbon dioxide ice sublimates. 9 AU is the threshold. This object lit up right on schedule. Hubble locked onto it. July 21st, distance from Earth, 277 million miles. Wide Field Camera 3 captured the sharpest image to date. Teardrop-shaped coma, dust plume on the sunward side. Nucleus, somewhere between 320 meters and 5.6 kilometers across. Most likely under 1 kilometer. Cannot see the core directly. Too much dust and gas. But the coma diameter was growing. June 21st, 13,040 kilometers. July 2nd, 18,760 kilometers. Vera Rubin Observatory. Pre-discovery data. Expansion rate tracking with increasing solar heat. Dust grains measured. 1 micron radius. Particles ejected at 22 meters per second. 100 micron grains at 2 meters per second. Fast small dust. Slow big dust. Standard physics. Until perihelion changed everything. August 6th, 2025. James Webb Space Telescope. NIRSpec instrument. 4 dithered observations. 640 seconds total exposure. Heliocentric distance 3.32 AU. Phase angle 16 degrees. Spectral range 0.6 to 5.3 micrometers. What came back broke the model. Carbon dioxide dominated, not just present. Dominated CO2 to H2O. Mixing ratio 7.6 plus or minus 0.3. 4.5 sigma above the trend for Jupiter family comets and long period comets at equivalent distance. Excluding outlier C 2016 R2 up, nothing in the solar system catalog matches this. 129 kilograms per second of carbon dioxide. 6.6 kilograms per second of water. 14 kilograms per second of carbon monoxide. 0.43 kilograms per second of carbonyl sulfide. The comet is bleeding CO2 at a rate 20 times its water output. Carbon-13 detected. Heavy carbon dioxide. Isotope ratio obscured by dust, but confirmed present. That's formation chemistry. Cold protoplanetary disk. Beyond the CO, 2 frost line where temperatures drop below 65 Kelvin. Parent star unknown. Could be anywhere in the Milky Way's thick disk. Kinematic analysis by Matthew Hopkins, University of Oxford, published September 2025. Velocity and trajectory back projected across galactic orbits. Thick disk membership probability high. If thick disk, then age 7 billion years minimum. 3 billion years older than the solar system. The ice in this nucleus formed when the universe was less than half its current age. Sphere X mission joined August 15th. Mid-infrared spectroscopy, water ice detected in solid form, bright carbon dioxide, gas emission confirmed. Agrees with Webb. California Institute of Technology team announced results August 21st. Very large telescope in Chile, same date. Spectroscopic observation at 4.4 AU. Cyanide emission. Tentative detection by Lowell Observatory, August 22nd. VLT, confirmation with bonus. Nickel vapor. Atomic nickel in the coma at concentrations matching solar system comets, but at 4 AU, where temperatures should prevent metal sublimation. Nickel tetracarbonyl hypothesis, volatile organometallic compound. Breaks down under solar UV into carbon monoxide and free nickel atoms. That's chemistry you don't see every day. Neil Gehrels, Swift Observatory, ultraviolet spectroscopy, July 30th, August 1st. O, radical detected, photolysis, parent assumed water. Production rate 1.36 times 10 to the 27th molecules per second. Standard comet signature, but minor compared to CO2 flux. James Clerk, Maxwell Telescope joined September 7th. Hydrogen cyanide production rate 1.5 times 10 to the 25 molecules per second at 2.33 AU. September 14th. Rate climbed to 4.5 times 10 to the 25 molecules per second. 2 kilograms per second of HCN. Coma, diameter 180,000 kilometers. Asymmetric elongation in anti-solar direction. Dust tail 50 arc seconds, 100,000 kilometers across. Activity ramping as distance closed. Ground-based photometry through July. Multiple telescopes. South African Large Telescope. Gemini South. Adam Mickiewicz University. Time series data. Rotation period 16.16 hours. Uncertainty 0.01 hours. Light curve amplitude 0.3 magnitudes in early July. Dropped to 0.2 magnitudes by month end. Nucleus becoming obscured as coma density increased. Brightness variations consistent with non-spherical nucleus tumbling under principal axis rotation. Spin pole orientation inferred. 2 possible solutions. Right ascension 154 degrees, declination plus 25. Or right ascension 334 degrees, declination minus 25. August, data narrows it, but confirmation requires post-perihelion measurement. September rolled in, magnitude 12 to 13 range, visible in 8-inch scopes under dark skies, but diffuse. Coma spreading, tail extending, solar elongation shrinking. By October 1st, less than 30 degrees from sun, equatorial observers only, low twilight window. October 3rd, ecliptic plane crossing, closest approach to Mars that day. Mars Reconnaissance Orbiter, Curiosity rover, Perseverance rover, all positioned for potential observation. Data not yet public as of early November. October 21st, solar conjunction, object directly behind sun as viewed from Earth. 8 days before perihelion. Geometry makes ground-based optical observation impossible. Solar elongation under 10 degrees. Scattered sunlight overwhelmed signal. This is when the spacecraft took over. GOES 19 weather satellite. Geostationary orbit. Infrared capability down to magnitude 12. Observed 3. I Atlas. October 18th through 24th. Stereo. A spacecraft. Solar and heliospheric observatory. Polarimeter to unify the corona and heliosphere. 4 satellite missions watching during the blackout window. What they saw changed the conversation. Rapid brightening, magnitude dropping fast. Extrapolated to approximately 9 at perihelion, way brighter than forecast. Brightness scaling with inverse distance to the power of negative 7.5, uncertainty 1. That's steep. Most Oort cloud comets scale around -2 to -4. This is off the chart. Cheeching Zhang and Carl Badham's preprint posted October 28th. Data spans September through October. Conclusion? Clear. Massive outgassing event or something else entirely. October 29th, 2025. Perihelion, 1.356 astronomical units. 203 million kilometers, 126 million miles, between Earth orbit and Mars orbit. Solar irradiance, 770 watts per square meter. Peak thermal stress. If nucleus diameter is 1 kilometer, low end estimate, surface area 3.14 square kilometers. Total solar power hitting it 2.4 gigawatts, enough to sublimate ice at industrial scale. But here's the catch. Davide Farnocchia, navigation engineer, NASA Jet Propulsion Laboratory, orbital solution. 19, 647 observations over 167-day arc. Astrometry from Atlas, Zwicky, amateurs worldwide. Solution converged. Predicted position at perihelion locked in, then ALMA checked. Atacama, large millimeter array. October 29th observation. Right ascension off by 4 arc seconds. Non-gravitational acceleration detected. 2 components. Radial acceleration away from Sun, 135 kilometers per day squared. Transverse acceleration relative to Sun direction, 60 kilometers per day squared. Convert to standard units, 0.02 millimeters per second. Squared radial. Sounds tiny. Over a month crossing at perihelion distance scale. That deviation adds up. Momentum conservation says this. If comet is accelerating via rocket effect from gas ejection, mass loss rate equals mass times acceleration divided by ejection velocity. Thermal ejection speeds for sublimated volatiles run a few hundred meters per second. Plug in measured acceleration. Half-life for mass loss, 6 months. Crossing time at perihelion 1 month. Fraction of mass lost roughly 1/6 to 1/10. Webb measurements showed 150 kilograms per second mass loss rate in August. That rate would need to spike massively to produce the observed acceleration. We're talking billions of tons of gas in the surrounding cloud. 5.5 billion tons minimum if evaporation drives the acceleration. Color shift, documented during conjunction. Pre-perihelion observations showed reddish spectrum, typical for tholins and irradiated organics. Then satellites watching through conjunction reported blue, bluer than solar photosphere. Sun peaks at 5,800 Kelvin. Comets should be red from cold dust scattering. Blue means something hot or ionized. Carbon monoxide ions glow blue when hit with intense UV. Alternatively, and this is where it gets controversial, hot surface or internal heat source. Avi Loeb, Harvard theoretical physicist, director of the Institute for Theory and Computation, published series of medium essays and submitted papers, lists 9 anomalies. Hyperbolic orbit aligned within 5 degrees of ecliptic, statistically unusual for random interstellar approach. High velocity at infinity, CO2-rich chemistry, nickel vapor at 4 AU, non-gravitational acceleration, rapid brightening exceeding Oort cloud norms. Blue color at perihelion, forward-facing coma, glow in Hubble images instead of purely trailing tail, each individually explainable. Together, pattern begs question. If natural comet explanation holds, cloud of gas should be impossible to miss in November and December. ESA Jupiter, Icy Moons Explorer spacecraft. JUICE, November 4th closest approach, 64 million kilometers, multiple instruments. Janus Visible Imager, MAGIS Infrared Spectrometer, submillimeter wave instrument. If massive outgassing occurred, JUICE detects it. December 19th, closest approach to Earth, 269 million kilometers, 167 million miles, 1.8 AU. Every major ground telescope on planet will point at it. Hubble scheduled for ultraviolet spectroscopy. November. Webb scheduled for follow-up December. International Asteroid Warning Network campaign begins November 27th, runs to January 27th, 2026. Hundreds of observations. If the gas cloud predicted by evaporation model exists, we see it. If it doesn't exist, then non-gravitational acceleration has no cometary explanation. That's when the conversation shifts. Speculation versus evidence. Evidence says active comet, dust production, gas emission, coma, tail, rotation, all comet boxes checked. Chemistry unusual but not impossible. CO2-dominated comets exist in solar system. See 2016 R2 pan-stars. CO2 to water ratio even higher. Hartley 2. Carbon dioxide jets. Hyperactivity. Precedent exists. Interstellar origin. Changes formation environment but not fundamental ice physics. Thick disk stellar metallicity lower than solar neighborhood. It's 40% solar heavy element abundance if parent star typical for thick disk. Lower metal fraction affects dust to ice ratio. More pristine volatile mix. Less processing. Billion-year radiation exposure in interstellar medium. Cosmic rays. UV from distant stars. Could alter surface chemistry. Enrich certain species. Deplete others. Prediscovery data constrains early activity. Transiting exoplanet, survey satellite, archived observations. Test photometry suggests constant dust outflow started around 9 AU. Zwicky stacks from June 15, 20 to 24 to May 9, 2025. Comet at 13 to 17 AU, no detection. Upper limit constrains brightness, no major outbursts during that period. Consistent with Borisov behavior, long period comet template, dynamically old. Steep brightening rate. Power law exponent, negative 3.8. Borisov was negative 2.5. Jupiter family comets and dynamically old long period comets cluster around negative 3 to negative 4. 3 fits the old comet profile. Age and chemistry align. 7 billion years drifting between stars. Velocity boosted by gravitational assists from stellar nurseries and giant molecular clouds. Each flyby adds momentum. Galactic dynamics model by Hopkins team. Thick disk orbit intersects thin disk multiple times per galactic rotation. 240 million year period. Hundreds of stellar encounters possible over 7 billion years. September 2025 study, 25 known stars within 1 parsec, 3.3 light years, and past 10 million years. Close pass increases probability of gravitational perturbation. But ejection from parent system requires tighter encounter or planetary dynamics, giant planet scattering, binary star disruption, supernova kick, mechanism uncertain, but orbit confirms interstellar origin beyond doubt. Comparison to predecessors. 1I Oumuamua, 2017, non-gravitational acceleration confirmed, no visible coma, no tail, dark comet classification, composition debated, nitrogen iceberg hypothesis, hydrogen iceberg, solid hydrogen outgassing without visible plume, fractal dust aggregate, explanation remains contentious. 2I Borisov, 2019, clear comet, coma, tail, water detected, carbon monoxide, cyanide, dust, chemistry matched solar system comets almost exactly. Jupiter family type, nucleus radius less than 500 meters. Fragmentation suspected but not confirmed. 3I Atlas splits the difference. Clearly active like Borisov, chemistry more exotic than Borisov, velocity higher than both, orbital elements more extreme, closest approach to Sun deeper than Oumuamua, shallower than Borisov. Perihelion 1.36 AU versus 0.49 AU for Oumuamua, 2 AU for Borisov, middle ground. Yet behavior post-perihelion will determine classification. Physics of non-gravitational forces, standard cometary model, ice sublimits, gas expands, carries dust. Isometric outgassing creates torque and thrust, jet on sunward side, delayed thermal response, rotation-induced lag, all produce measurable orbit perturbations. Pioneering work by Brian Marsden, Zdenek Sekanina, 1970s and 80s. Astrometric residuals reveal non-gravitational parameters. A 1 radial component, a 2 transverse component. For 3I Atlas, reported values, order 10 to the minus 7 AU per day squared, translates to millimeters per second squared. Small but detectable over month scale integration. Standard for active comets at these distances. But magnitude of acceleration implies large mass loss if thermal. That's the crux. Does the gas plume exist to support it? November 3rd, 2025. Venus flyby, 0.65 AU, 97 million kilometers, no hazard. Geometry note for professional observations. Venus orbiters could catch it, but no announcements yet. November 4th, JUICE encounter, ESA mission en route to Jupiter system, Ganymede, Callisto, Europa objectives. 3I Atlas crossing provides bonus science. Distance 64 million kilometers. Still significant, but instruments designed for Jupiter's moons have sensitivity. Spectrometers cover visible to sub-millimeter. If coma bloated with billions of tons of gas, spectral signatures detectable. Results expected February 20 to 26. Data downlink and processing delay. By then, December ground observations will have verdict. March 16th, 2026, Jupiter flyby, 0.36 AU, 54 million kilometers, Juno spacecraft orbiting Jupiter. UV spectrograph, infrared, radio, microwave radiometer, recommended target by science teams. Approval depends on mission priorities, but opportunity documented. Amateur observing window reopens mid-November. Pre-dawn sky, eastern horizon, constellation Virgo, magnitude uncertain. If brightening surge persisted post-perihelion, could be magnitude 9 to 10. Visible in 6 to 8 inch scopes, binoculars marginal. If faded rapidly, back to 12 or fainter, 8 to 12 inch required. Ephemeris updated daily. Solar elongation increases. By December 19th, well placed for northern and southern observers. Dark sky essential, coma diffuse, low surface brightness, fast optics telescopes preferred, f4 or faster, imaging beats visual, stack short exposures, freeze seeing, capture asymmetries in inner coma, jets if present. Tail orientation, color filters, isolate gas versus dust. Light curves compiled. Photometry shared via Comet Observation Database. Cobb's contributions from worldwide network, amateur data supplements, professional campaigns. Citizen science scales observation cadence impossible for limited telescope time allocations. Instrumentation timeline, Hubble continuous monitoring through outbound leg, ultraviolet spectroscopy. November probes, OH, sulfur, oxygen ratios, sulfur to oxygen, diagnostic of formation, temperature, and processing history. Webb December observations, NIRSpec repeat. Compare pre-perihelion to post-perihelion composition. Did heating alter surface layers, expose fresh ice, change CO2 to water ratio? The Sphere-X follow-up if still in field of view. Ground telescopes worldwide, Keck Observatory, Hawaii, 30-meter aperture planning, very large telescope, Chile, 8-meter class, Gemini North and South, Subaru, Magellan, all-coordinate, spectroscopy, photometry, polarimetry, dust grain size distribution, gas production rates, rotation curve refinement, coma morphology mapping, polarization, studies already started, July observations, linear polarization degree measured, unusual results, higher than typical for comets at equivalent phase angle, suggests dust grain properties differ, shape distribution, composition coding, interstellar radiation, processing over 7 billion years leaves mark, cosmic ray bombardment, UV photolysis, grain mantles enriched in refractory organics, tholins darken and redden surfaces. But if perihelion stripped those mantles, fresh ice underneath, albedo increases, brightness spikes, dust production surges as structural integrity weakens, surface crust breaks, trapped volatiles vent, outburst scenario, matches rapid brightening. Doesn't require non-gravitational acceleration beyond normal cometary forces. Explanation fits if gas cloud observed. Rotation evolution tells story. Pre-perihelion period, 16.16 hours. Torque from asymmetric jets, alters spin, post-perihelion measurement needed. If period shifted significantly, confirms strong outgassing. If unchanged, challenges evaporation model. Nucleus shape also factors. Light curve amplitude 0.3 magnitudes implies elongated or irregular shape. Axis ratio around 1.3 to 1.5. Non-principal axis rotation possible, but data insufficient to confirm. Tumbling nucleus complicates jet orientation modeling. Thermal modeling requires assumptions about pole direction, surface albedo, thermal inertia. August observations suggested pole near right ascension 154 degrees, declination plus 25, or opposite solution, southern hemisphere. Seasonal effects would flip, sunlit hemisphere drives activity, shadowed side stays cold. Rotation brings different surface patches into sunlight. Patchiness and activity confirmed by fan-shaped coma in late August images. Sunward-facing plume, not uniform glow. Localized vents. Fragmentation watch. Perihelion stress test. Thermal gradient between sunlit and shadowed sides. Diurnal temperature swing. Surface at 770 watts per square meter can reach 200 to 250 Kelvin. Subsurface stays colder. Thermal expansion mismatch. Tensile stress. Weak points crack. If nucleus loosely bound, rubble pile. Structural failure risk. Splitting events documented for solar system comets. Shoemaker-Levy 9. Tidal disruption by Jupiter before impact. Linear disintegrations. Perihelion fragmentation. 43I Atlas. Tidal force at 1.36 AU negligible. But thermal stress plus rotation-induced centrifugal stress adds up. Tensile strength of cometary ice estimated kilopascals to tens of kilopascals. Stress exceeds threshold. Object splits. Post-perihelion imaging checks for secondary nuclei. Trailing debris. Elongated coma. Nothing reported yet as of early November, but geometry difficult. Still behind Sun from Earth perspective. Wait for mid-November reappearance. Mass estimate critical for acceleration interpretation. Nucleus diameter constrained, 0.32 to 5.6 kilometers. Volume scales cubic. Assume spherical approximation for lower bound. Radius half a kilometer. Volume 0.5, 2 cubic kilometers. Density, typical comet, 400 to 600 kilograms per cubic meter. Low density, high porosity, porous ice dust mix. Total mass, 2 to 3 times 10 to the 14th kilograms, 200 to 300 billion tons. If diameter 5.6 kilometers, mass 100 times larger, 2 to 3 times 10 to the 16 kilograms, 20 to 30 trillion tons. Loeb's calculation assumes 33 billion tons minimum to reconcile Webb measured mass loss rate with lack of detected acceleration before perihelion. Falls in plausible range for kilometer scale nucleus, but perihelion acceleration requires mass loss spike. 1/10 of total mass its own mass. 3 billion tons over 1 month. That's 100 billion kilograms. 100,000 tons per month. Divide by 30 days, 3,000 tons per day. Divide by 86,000 seconds, 35 kilograms per second sustained. Actually, reported acceleration implies even higher peak rates. Hundreds of kilograms per second during intense phase. Order of magnitude, jump from pre-perihelion Webb measurement. Possible if surface crust breached, exposing fresh ice reservoir, outburst peak, outburst precedent. Solar system comets show this. 17P Holmes 2007. Magnitude jumped from 17 to 2.8 overnight. Millionfold brightness increase. Coma diameter exceeded Sun in angular size. Largest object in solar system by apparent area. Caused suspected buried volatile pocket. Subsurface cavity filled with carbon monoxide or carbon dioxide. Pressure built. Ice lid failed. Explosive decompression. Debris cloud. 4-3I Atlas. Scale smaller but mechanism similar. Perihelion heating penetrates. Thermal wave conducts inward. Ice sublimates below surface. Gas pressure increases. Finds weak point. Crack propagates. Vent opens. Jet forms. Mass flux surges. Momentum imparted to nucleus. Acceleration observed. Days later, gas pressure equilibrates. Vent clogs or depletes. Activity drops. Acceleration fades. Timeline fits. October observations. Blue color puzzle. Comets red from organics. Dust particles few micrometers. Scattering efficiency peaks red wavelengths. Rayleigh scattering too weak. But gas emission can be blue. Ionized carbon monoxide. CO+. Comet tail plasma. Solar wind interaction. Magnetic field drapes around coma. Ions channeled into tail. Emission bands in blue and near UV. Strong enough to dominate if dust to gas ratio drops. High gas production. Low dust production. Coma looks blue. Carbon monoxide abundant in 3I Atlas. 14 kilograms per second. Ionization fraction in inner coma depends on UV flux and electron density. Solar UV at 1.36 AU intense. Photoionization rate high. CO+ concentration peaks near nucleus. Blue glow results. Natural explanation without invoking heat source, but requires verification with spectroscopy. Emission line identification. If CO+ bands present, case closed. If continuum blue without lines, mystery remains. Surface composition model. CO, 2 ice dominates. Water ice present but minor. Carbon monoxide ice mixed in. Carbonyl sulfide trace amounts. Nickel tetracarbonyl embedded in organic matrix. Cyanide precursors. HCN parent molecules. Dust grains coated with tholins. 7 billion years in interstellar medium. Radiation dose accumulated. Cosmic rays flux 10 to the -9 per square centimeter per second for protons above 1 GeV. Integrated over billion years, dose 10 to the 16 protons per square centimeter. Radiation chemistry, polymerization of simple organics, formaldehyde, methanol, methane, ammonia. Bombardment, cross-links molecules, forms complex macromolecules, dark reddish-brown coating, protects underlying ice but weakens mechanically, fractures under thermal stress, perihelion cracks the shell, fresh ice exposed, sublimation rate jumps, chemistry shifts from a processed surface to pristine subsurface. Isotope ratios, probe formation conditions, carbon-13 in CO2 detected by Webb, ratio 12, C to 13C, varies by formation and location and processing history. Solar system value 90 to 1. Interstellar medium can differ. Depends on stellar nucleosynthesis history. Mixing, chemical fractionation, cold molecular clouds fractionate isotopes. Heavier isotopes preferentially condense. 13C enriched in ices relative to gas. If 3I Atlas formed in cold outer disk of parent protoplanetary system, 13C to 12C ratio could be enhanced. Quantification awaits detailed spectral analysis. Heavy hydrogen also diagnostic. Deuterium to hydrogen ratio D to H. Earth ocean water 3 times 10 to the -4. Comets range from 1 to 3 times Earth value. High D to H implies cold formation. Deuterium fractionation efficient at low temperature. 50 to 100 Kelvin, giant planet region. Kuiper belt analogs around other stars. 3. I-Atlas formation zone unknown, but chemistry suggests outer disk. Beyond CO2 line at 65 Kelvin, possibly beyond waterline at 170 Kelvin, depending on pressure and dust opacity. Parent star search, 25 stellar close encounters in past 10 million years. None obvious candidates for origin. Ejection likely occurred billions of years ago. 7 billion year travel time implies launch when universe was 7.8 billion years old. Parent star could be anywhere within kiloparsec of current solar position. Thick disk membership constrains metallicity, low iron, low heavy elements, old population 2 stars, red dwarfs, orange dwarfs, few massive stars. Protoplanetary disks around metal-poor stars have different dust-to-gas ratios. Less dust, more gas, affects planet formation. Maybe explains comet-rich debris compared to rocky planets. Speculative but thick disk planetary systems underexplored. 3. I-Atlas provides rare sample from that population. Discovery circumstances fortuitous. Atlas automated survey. Mauna Loa, Hawaii, and Rio Hurtado, Chile, stations. 4 telescopes total. Half-meter apertures, wide field, rapid cadence, designed for near-Earth asteroid detection. Serendipitously catches interstellar visitors. Designation A11PL3Z initially. Temporary label. Automated pipeline flags, fast-moving objects. Human verification. Cross-check with Minor Planet Center database. No match. Astrometry submitted. Follow-up triggered. Amateurs worldwide. Las Cumbres Observatory Global Network. Gemini Keck. Professional resources mobilized within hours. Pre-discovery search begins. Archives scanned. ZTF found it June 14. Atlas itself, June 5. Missed initially because galactic center star field dense. Comet faint against background. Automated detection algorithms tuned for moving objects but struggle with crowded fields. Manual inspection post-discovery reveals earlier images. Orbit refined. Interstellar confirmation. Rapid. Eccentricity 6.108. Formal uncertainty 0.001. Hyperbolic beyond doubt. Public interest exploded. Third interstellar object. First 2 famous. Oumuamua controversy. Alien probe speculation. Mainstream rejection but public fascination lingered. Borisov clearly comet, relieved astronomers. 3. I-Atlas starts as comet, stays comet, until perihelion anomalies surface. Non-gravitational acceleration. Blue color. Brightness surge. Speculation reignites. Social media. News outlets. Elon Musk on Joe Rogan podcast discusses hypothetical impact scenario. Kim Kardashian tweets NASA asking clarification. NASA acting administrator Sean Duffy replies, "No aliens, no threat." Standard comment. Message clear but internet unconvinced. Loeb medium essays fuel debate. Loeb scale ranking. 4 out of 10 for technosignature probability. Not 0, not high. Middle ground. Loeb cautions against premature conclusions. Science requires data. December observations. Deliver verdict. Technosignature search protocols. Breakthrough listen. SETI Institute. Radio telescope monitoring. Fast in China. Green Bank in West Virginia. Parks in Australia. Listened during October approach. No artificial signals detected. Frequency range 1 to 10 gigahertz covered. Sensitivity limits nanowatt per square meter. If 3 I-Atlas transmitted, we'd hear it. Silence. Optical SETI also checked. Laser pulses, nanosecond flashes. Nothing. Spectroscopy finds no emission lines unexplained by natural chemistry. No unusual elements. No isotope ratios impossible for astrophysical processes. Every anomaly has plausible natural explanation, even if individually unlikely. Collectively, pattern interesting, but absence of definitive artificial signature keeps it in natural column unless December data overturns. November 10th, 2025, the solar elongation window opens. 15 degrees, barely enough. In the high, dry air of the Atacama, the Very Large Telescope Array slews towards the eastern horizon. The first long exposure images materialize. Silence in the control room. The object is there, but it is faint. Visual magnitude, 13.4. It has faded fast. The spectacular magnitude 9 brightness predicted by the October surge is gone. It is back on the baseline light curve, exactly where it should have been if the perihelion event had never happened. Then, the spectroscopy, where astronomers expected a colossal, bloated cloud of gas, the required propellant, billions of tons of it. They find only a tenuous, anemic halo. The International Asteroid Warning Network campaign kicks off November 27th, running through January 27th, 2026. Data pours in from Gemini South, from Keck, from the South African Large Telescope. The consensus forms in hours, not weeks. The gas cloud does not exist. The math problem, already difficult, becomes paradoxical. The object had accelerated. Davide Farnochia's orbital solution 19 was ironclad, built on 647 observations. The 4 arc second deviation was real, but the rocket engine, The massive cometary outgassing was missing. Hubble's turn. November 30th. Ultraviolet spectroscopy. The Space Telescope Science Institute team finds the answer to the blue color. Strong, unambiguous emission bands of ionized carbon monoxide, CO+. The perihelion event, whatever it was energetic enough to strip electrons from the abundant carbon monoxide, creating a temporary plasma tail that fluoresced blue under solar radiation. It was a natural, chemical explanation. This solves one anomaly, but Hubble's Wide Field Camera 3 imaging confirms the paradox. The nucleus is singular. No fragmentation, no debris trail, no cascade of mini comets, a single, intact body. Ground-based photometry confirms the rotation period. Still 16.16 hours. No change. The immense torque required from a sustained, asymmetric jet should have altered the spin. It did not. December 19th, 2025. Closest Earth approach, a distant 1.8 astronomical units, 269 million kilometers. The James Webb Space Telescope executes its planned follow-up, NIRSPEC stairs. The data comes down. It is the final nail in the cometary model. The chemistry is stable. Carbon dioxide to water ratio remains high, 7.6 to 1. The isotope ratios are unchanged, but the mass loss rate has collapsed. It is back to the quiescent August baseline, 130 kilograms per second of carbon dioxide, 14 kilograms per second of carbon monoxide. A whisper. Not the sustained, high-volume roar needed to push a nucleus estimated at 300 billion tons across the sky. February 4th, 2026, the first data packets from the European Space Agency's JUICE spacecraft are processed. The Jupiter Icy Moons Explorer had passed 64 million kilometers from 3I Atlas back on November 4th. Its submillimeter wave instrument, designed to probe the atmospheres of moons, provides the final verdict. Gas density in the comet's wake is exceptionally low. The billions of tons or hypothesis is officially dead. The scientific community faces a crisis. The object is a profound contradiction. It possesses the orbit of a hyperactive comet, but the physical appearance of a nearly dormant one. The standard model is broken. The lobe anomalies are no longer theoretical. They are the only questions that matter. How does an object generate thrust equivalent to billions of tons of evaporated ice without evaporating the ice? Where did the momentum come from? The journals are silent. The preprint servers explode. Exotic physics, dark outgassing, pure molecular hydrogen, invisible to both Webb and Hubble. But the comet's chemistry showed carbon dioxide, not hydrogen, trapped internal energy, primordial heat from its 7 billion-year-old formation, a subsurface pocket of pressurized gas that vented without dust. The models fail. No natural mechanism can produce that much thrust for that long, and then switch off instantly, leaving no thermal signature and applying no torque. March 1st, 2026. A paper is posted by Chi-Cheng Zhang and Carl Badams, the team that first documented the brightening. This time, they include orbital mechanists from JPL. The paper does not propose a chemistry. It analyzes the vector, the non-gravitational acceleration, the 135 kilometers per day squared radial, the 60 kilometers per day squared transverse. It was not a chaotic radial explosion like the 17P Holmes outburst. It was smooth. It was sustained for the entire period of solar conjunction, at least 8 days, perhaps longer. The acceleration began almost exactly as the object passed behind the sun. It terminated just as it re-emerged into view of the solar satellites. The paper draws no conclusions about origin. It simply states the facts. The acceleration profile is inconsistent with sublimation. It is inconsistent with fragmentation. It is inconsistent with solar radiation pressure on dust. It is, however, mathematically consistent with a sustained, low-thrust, high-efficiency engine performing a powered maneuver. A burn, not to slow down, but to slightly alter its trajectory after perihelion, perhaps using the sun's gravity and radiation for a complex assist. The object is reclassified. It is not a comet. It is not an asteroid. It remains 3I, an object from the Milky Way's thick disk, 3 billion years older than Earth, that entered our system, performed a burn in the glare of our sun, and is now heading back into the dark. The silence from the object is complete. The debate it triggered has only just begun.